start recording. First, you mute everyone. Yep. So, hello everyone. Today we have the great pleasure to welcome Professor Nader Engheta, who is really famous, as everyone knows. So he's from the University of Pennsylvania. He has contributed a lot to metamaterials, and today he's going to talk about space-time, so four-dimensional metamaterials for wave propagation and diffusion phenomena. Professor Engheta.
Thank you so much. Let me share my screen. 1 second. Thank you very much, Sebastian, for the introduction. I'd like to thank the organizers, Bogdan, Sebastian, Muammer, and all the members of their teams, for putting this series of colloquia and seminar together. It's a great pleasure for me to be part of this, and I'm very thankful and I'm very honored and pleased to be here. Thank you very much. In the talk today, I would like to present some of an overview of one of the areas of research activities that's going on in my group, and that is how to take advantage of the fourth dimension of time in order to manipulate waves and diffusion. Now, obviously, a lot of metamaterial works shows that there's a lot of interesting wave phenomena is being tailored using spatial inhomogeneity. But adding the time has become one of the very interesting topic recently in many groups, and here we would like to see how addition of the temporal variation of the material parameters instead of or in addition to the spatial variation of the parameter can help us to manipulate waves and diffusion phenomena. Now, why are we interested in this, by the way? So in addition to the fact that that will give you an additional degree of freedom to control the wave, we were also inspired by two phenomena. One was the idea of time crystal that was introduced by Nobel laureate Frank Wilczek in 2012. And he said that when we look at the regular crystal, which is the periodic distribution of the atomic structure in space, he mentioned what would happen if we look at the periodic distribution in time. In other words, kind of like a time crystal idea that he proposed. And this created a lot of interest and debates in the community. And then about 3-4 years ago, two experimental groups, Michelle Lukins from Harvard and Chris Monroe from University of Maryland, experimentally indeed showed the idea of time crystal that Frank Wilczek mentioned. Another activity that really inspired us is by my friend Matthias Fink and his group, that he showed how, the variation of, in this case, the water wave that he's so beautifully shown, in his paper of Nature Physics, that creates the time reversal. And so these works really excited us and motivated us to look into what we can do with regard to the temporal aspects of metamaterial. 1 second, let's see. Did something show up in the remote control? Sebastian, did you have something that your WebEx creates that? Let me see. Because it shows on my screen. Do you see that in your screen?
No, we don't.
We don't see it.
Okay, so let me just put it aside. I don't want to touch it because I don't want to stop the things there. Okay. And of course, the time-dependent, let me see. The time-dependent platform in electromagnetics has a long history. Here, I'm just mentioning some of the activities that goes back actually to 1950s by the work of Morgenthaler, who showed that if you have wave propagation in a medium and you rapidly change the phase velocity of a medium by changing the index of refraction, how the wave actually behaves there. And over the years, there are a lot of activities. And of course, this is not an exhaustive list, and there are many, many groups, working in this area. So before I get to specifically what we are working on, I would like to give, some basics and background material as to what happens in the temporal domain of material changes. Now, if we look at the very simplest possible spatial inhomogeneity that we teach to our student, and that is basically a simple inhomogeneity, a boundary between two media, one medium to the left and the other medium to the right, and you have a Fresnel problem, which is a standard problem that we always teach our student. The temporal dual of that is that if you assume you have an unbounded medium, as the wave already in the medium is propagating, and then you rapidly change the permittivity at a given time, then this becomes the dual of the Fresnel in the time domain. Now, what are the interesting boundary conditions that we should consider? And this has been studied, by the way, in the literature extensively. Again, by analogy to the Fresnel, we know that if we have a spatial boundary between two media, and we look at Maxwell's equation, source-free Maxwell's equation, we teach our students that in order to find the boundary condition, we have to make sure that the spatial derivative would stay finite. So as a result, at the boundary, we will have the standard boundary condition that tangential components of H and E should be continuous, and the normal components of B and D should be continuous in the source-free scenario. So what is the temporal dual of this type of boundary condition? Similar philosophy applies over here, is because if you look at Maxwell's equation source-free, we need to make sure that the temporal time that involves in that, the temporal derivative stay finite. So as a result, when you rapidly change the permittivity, you need to make sure that the vector D just before the change and just after the change stay the same. And as a result of that, for the same thing for the vector B, so as a result of that, you get this boundary condition, temporal boundary condition between the epsilon1 and epsilon2 and electric field that you have there. I have to point out over here, by the way, that this is an approximation, because strictly speaking, when we are in the time domain, the expression of D equal to epsilon E should have the form of a convolution. Now, when we write D equal to epsilon E, that's in the frequency domain. So when we are in the time domain, strictly speaking, we have to write a convolution between E and D. And as a result, one needs to take into account the dispersion of the material. And indeed, that's one of the areas that in my group we are working on. And we get some interesting results by adding the dispersion into it. But for now, by the way, I'm assuming that this rapid variation of permittivity follows this approximate expression that we say over here, because you can show that if the resonance of the material is far away from the operating frequency of the wave over here, then approximately you can express this one here. For the rest of my talk, I'm using this approximation, but I would like to point out that dispersion can also play a very important role. So what is the relationship between frequency and wavelength in temporal metamaterial? Several groups in the past have shown this relationship. Here I'm referring to Govan Agrawal work that he showed that, again, is an analogy with the Fresnel. If you have a wave coming here between two linear medium in space, this is two semi-infinite medium in space, obviously the frequency omega-1 is the same as omega-2. In other words, the refracted wave has the same frequency of incident wave, but of course the wave numbers are different and the wavelengths of them are different. The temporal dual of that is the following way, that if you have an unbounded medium and you have a monochromatic wave with the frequency omega already in this medium, if you rapidly change the permittivity, then the wave number, the wave vector would stay the same. So as a result, the frequency has to change. And this is something known in the plasma physics community as photon acceleration that you would have there. The consequence of that is quite interesting, because as Agrawal have shown, obviously, and also other people have shown too, Agrawal was not the only one that looked at this, but you have this wave number equality should hold true, which means that when you have a single monochromatic propagating in a medium with the omega-1 frequency and K1 wave number. When you do this rapid variation of permittivity, you create two waves, one of them forward-going wave, the other one is backward-going wave. And you notice, by the way, in this expression, K1 stayed the same, but then omega 2 would be different than omega 1, and you have a coefficient for the backward wave, and you have a coefficient for the forward wave. So the expression for this forward wave and backward wave coefficient is derived by previous groups. Agrawal is one of them, that you can write it in this form over here. One thing I'd like to point out, by the way, here, that in many situations, this backward wave is annoying, is nuisance. And I'm going to talk about how we can actually get rid of this backward wave. And in fact, towards the end of my talk, you're going to see that how we can take advantage of this backward wave in some scenarios that we have there. Now, so let me show you, just to build intuition for those of you who may be less familiar with this temporal aspect, is that if you look at this simple wave packet propagating in boundary between two spatial media over here, you get the standard Fresnel refraction and reflection. You notice that the wavelength, of course, is different. Naturally, this is what we do every day. But when you look at the temporal one, you notice how the original wave packet that's propagating over here split into the forward wave and backward wave. And you notice that when it splits, actually, the wavelength does not change. If you look at this, you notice the wavelength stay the same, but the velocity of propagation become different. So as a result, if you're sitting at one point in this medium and you see this variation of permittivity, you notice that at that point, your frequency is changing, obviously. So these are all already very well known, in the literature, and many groups have worked on them. So what is it that we are interested in my group to look at this? One of the earlier work that we did was to see whether we can have an interesting analogy between some of the well-known phenomena in spatial domain to see whether we can have a temporal version of that. And one of those things is the idea of anti-reflection coating. Now, we're all familiar with anti-reflection coating in the standard, problem. And that is, if we have two medium in space, so the permittivity is a function of space over here, two media, and you send a wave over here, obviously we get some reflection and we get some transmission. And the reflection in many situations is not desirable. So we would like to eliminate that reflection. And the standard technique that the people have used for decades is a layer in between there, known as anti-reflection coating there. And the thickness of this coat and the permittivity of the coat follows a certain standard, expression that we're all familiar with that. And if we do it properly, then in that case, reflection will become zero. That is known, of course, the AR coating or anti-reflection coating. Do we have a temporal version of that? Yes, indeed we have. If we have an unbounded medium, the wave is propagating through that, and we rapidly change the permittivity, as we just showed, a few slides ago, then you get a backward wave and forward wave, and we don't want that backward wave. So what we were thinking about is it possible to actually change this rapid variation in two steps rather than in one rapid variation? So essentially what that means is that can we actually change the permittivity from epsilon 1 before we get to epsilon 2, we change it to some intermediate aspect. And what should be that intermediate epsilon, and how long should we keep it in order to get the backward wave eliminated? And indeed, as expected, you're going to get very interesting analogy between the two phenomena. This is the standard spatial quarter wave that you're all familiar with the permittivity being the geometric mean of epsilon 1 and epsilon 2, and the thickness should be lambda over 4, or lambda over 4 plus multiple of lambda over 2, whereas in the temporal version of that, you get something that, of course, temporally expected, and that is this epsilon equivalent, again, is a geometric mean between the two, but you notice that the delta t that we have to hold this would be basically equivalent of the quarter period rather than the quarter wavelength scenario. Now become quarter period of that. And indeed, we can see that, in the simulation. This is the standard two media, the wave packet coming over here, you get the reflection and the boundary. And if you look at the content, obviously in the case of the spatial domain, the frequency doesn't change. As you see over here, the frequency stays the same. And if you put a thin layer of standard anti-reflection coating, you notice that the reflection would stop, and that's the standard coating. And if you look at the content of the reflected wave and transmitted wave, you see that the reflected wave, of course, becomes zero. That's expected in the standard anti-reflection coating. But let's do that now in time. In time, so in order to show that that basically the quarter period, temporal coating, we show it over here as a function of time, how the permittivity changes. So permittivity changes at this point, go to this one shot. Obviously, you see that you get a backward wave that's coming over here. But if we go through the one additional step with the proper delta t, you're going to get it. By the way, one thing I would like to point out, and you notice, by the way, when we look at the reflected and transmitted wave, of course, the frequency will be different than the original wave, as expected. And now let's put that delta t, or quarter period, if you will, over here, and you notice that the backward wave disappeared. Let this simulation run again, and you will see that from the beginning of it. It comes over here, and then you go through two steps, and you notice that this will not happen. By the way, one thing is, of course, also it's expected over here is that if instead of going through these steps, we actually change the permittivity gradually, obviously the backward wave is also stopped. That would be equivalent of having in the spatial domain, the wave is coming from one medium to the other medium through the very gradual variation of the permittivity. Same thing happened in temporal one. But in the temporal one, we have to make sure that while that variation of permittivity happens, the wave is always in your medium. And that's, of course, one of the interesting challenges, because, of course, wave goes very fast. So we have to make sure that the wave stays there. So one way that we are addressing that issue is through creating ring resonators. So the wave stays in the ring, and that changes will happen there. You might say, okay, up to now, we are assuming that the medium is unbounded. But practically, of course, we don't have unbounded medium. So can we actually bring the space variation here as well? And the answer is yes, actually, we can do that. So if your wave packet has a certain, spatial extent, then obviously you don't need to change the entire medium. So imagine here in spatial domain, you have a region that it's fixed and it's not changing in time. You have another region over here that's not changing in time. And only certain region in front of this is the one that is permittivity changes. In that case, you can achieve these things again. So as the wave packet comes and gets into this region, then you're going to change this permittivity in the anti-reflection coating temporal one. And in that case, there's no need to change the entire medium. And this works also quite nicely over here, as our simulation shows over here. By the way, this actually reminds me kind of like the way, the Panama Canal locks work. If you look at the engineering of the Panama Canal, is that when the ship comes over here, goes through this lock, the lock closes and the level of the water will come up. And then the other lock opens and the ship goes to the next one and the level of the water come up and so on. And eventually the ship essentially can go from this side to that side. So it kind of reminds me that by changing the permittivity in time, we can actually basically carry the wave to the other side without having the reflection. So that's what one of the early works that we did on this temporal or four-dimensional metamaterial. And you notice that we have a combination of space and temporal scenario. But one of the things that have been of interest to us is that yes, of course, there's an interesting analogy between time and space, and we know that from Maxwellian electrodynamics. But is there any? But of course, there are also interesting differences. For example, of course, the time, we have to make sure the causality holds, obviously. In the space, we have three dimension, you know, in the real space that we live, and plus the time. So it looks like, of course, time is one dimension, and the spatial dimension is the three. Is it possible that we can actually increase the degrees of freedom of the time? So that's what we started thinking about, this concept of temporal anisotropy. And what do I mean by temporal anisotropy? You notice that the change from permittivity to another permittivity that we have talked so far was from one isotropic scenario, mean one permittivity, to another isotropic scenario, mean another permittivity. So both of them scalar. But what if we ask the following question, that can we actually change the medium temporally from an isotropic medium to anisotropic medium? In other words, you would change the permittivity to two different values depending, you know, on the element of epsilon along the certain axis. So in other words, you make the medium anisotropic, birefringent, or uniaxial and biaxial. So what would happen there? Now, we know that when we do this, the wave vector or wave number should stay the same. But here's an interesting scenario, because these boundary conditions, as I mentioned, should hold true. Again, I'm assuming over here that the dispersion is not here, and the resonance of the medium is very far away from the operating frequency. And we are all familiar with index of ellipsoid, you know, in birefringent medium. So essentially what we have is that you start with an isotropic medium whose index is the form of, sphere of index, changing it to an index ellipsoid that you have there. Now, depending on the original direction of wave propagation, which is represented by wave vector k, when you make that change, you need to make sure that the k would stay the same before and after this change. So what else should change? Well, in the previous case, we showed that the frequency should change. Well, the same thing happens over here. But here's an interesting point, is that depending on the direction of propagation, the difference between the indices will be different when we go from isotropic to anisotropic one, because the birefringence would give us a different index depending on the direction of propagation. So what does that mean? That means we have two interesting phenomena over here. Number one is that depending on the direction of propagation, the change in the frequency will be different. So if you start with the original wave that goes, let's say, spherically in all directions, when you actually change the permittivity from isotropic to anisotropic one, the wave in different direction would have a different frequency. You started with monochromatic signal, but you end up with polychromatic signal depending on the direction of propagation. Another interesting feature, by the way, is the fact that because you are going from the scalar epsilon1, if you see the cursor on my screen, to the tensorial epsilon2, the orientation of the electric field will change too. So not only the value of electric field would change, the magnitude of that, but also the orientation of electric field changes, which means the direction of the Poynting vector will change from the previous case. So in that case, you will have a scenario that the direction of the phase flow is different than energy flow, which, by the way, that's the case, of course, in an isotropic medium. But this will give us the possibility that you can actually change the energy flow kind of midstream that you have there. So the first scenario of the different frequency and different direction of propagation was worked out by Christoph Kallos, and in his paper in Optics Leather, that he calls it inverse prism. So in other words, if you start with the wave in different direction, you're going to have different frequencies after this rapid change of permittivity. So we decided to look at the other issues, in other words, the energy flow variation. So imagine that you have an antenna. So I'm going to show you, by the way, in simulation in the left side of the screen. Imagine that you have an antenna that's oriented 45 degrees over here. And this antenna, of course, will give rise to the standard, radiation pattern that, it's maximum in the equatorial plane that have. But as this wave is propagating away from the antenna, what we're going to do, we're going to change the permittivity from epsilon1 to two numbers, epsilon2 XX for the electric component in the X component, and epsilon2 YY, two different numbers. in the Y component. And you're going to see what happens to this wave packet that's coming out of the antenna. Rather than keep going in that direction, it's going to change midstream, the wave propagation. So this is the original wave that's coming from the antenna. And when you do change that, you notice that the wave, rather than going through the 135 degrees that's going, at minus 45 and 135 that's going, is going to actually start changing towards left and right. And whether that direction would be left and right or up and down depends on the relative value of this epsilon 2x, epsilon 2y, with respect to each other. So for example, here is the repeat of that simulation, but you notice that now the wave packets is going in different directions because the epsilon 2x, epsilon 2y is chosen with the different relative values there. So this actually helps us to come up with the following idea. Is it possible to actually extend the idea of beaming, or in like a phased array, to a temporal beaming, which we call it temporal aiming? What do we mean by that? So ordinarily, when you have an antenna, as you all know, if you have an antenna over here and you have a beam that's coming in this direction, and you have two receivers sitting over here, if you like, the beam goes toward receiver 1 versus receiver 2, you can two things you can do. Either you can actually changes the phase of this array, like a phased array concept, or if you are on the movable stage, the antenna can move in the movable stage in order to put the beam in the direction you want, just like what you see in this cartoon that we show over here. Now, but what would happen if we don't have the luxury of either doing it the phased array or doing it the moving things? For example, imagine that you have your source embedded, particularly in integrated photonics, that your source is embedded in a substrate. And you would like to change the direction of the wave packet towards the detector that you want. How do we do that? Can we use this concept of temporal anisotropy to do this? So if we start with the isotropic substrate and then you change it to anisotropic substrate for this, in a sense, the direction of the phase flow previously was in the direction of the energy flow, which was, let's say, original angle theta 1. But after you do this change, the direction of phase flow stayed the same, but the direction of the energy flow would be different than that. So essentially, we would have a possibility to temporally have a beam go towards the detector you like to have in the substrate. So we did the analysis on this. I don't want to bore you with the detail of the mathematics, but if you actually follow that, you notice, depending on angle of incidence and the relative values of the permittivity before and after the change, the direction of the Poynting vector can actually follow these analytical formulas. And these are some, analytical distribution of the field you see. For example, in this case, the original plane wave, it shows, by the way, the color shows the phase variation, and the vector, the black arrows shows the direction of the Poynting vector. You notice when you make this change over here in the second, by the way, let me use my laser pointer, that might be better over here. So you see that the direction of the energy flow is different than the direction of phase flow, depending on the changes that you make over here. So here, for example, we apply this concept into a Gaussian wave distribution. Imagine that you have this Gaussian wave with a waist of 9 wavelengths coming in some arbitrary angle, 25 degrees. And when the midstream, you change the permittivity from isotropic to anisotropic one, you notice that the Gaussian beam actually starts moving sideways rather than going in the direction we want. You notice, by the way, that here we also have a little bit of backward wave, as I mentioned to you that previously. You're going to see how we can get rid of this as well. If you change the waist of your Gaussian beam to a smaller waist, then obviously you notice this even more prominently as to how this thing varies like that. We said this interesting can be used, in real time. You can actually guide, or temporal guiding, if you will, of temporal aiming of your wave packet. So here in the next slide, I'm going to show you a series of simulation for the wave packet that's coming from the source. Originally, it's planned that this wave packet to go to the detector 1, but if you like, midstream, you can change the permittivity of the medium in which the antenna is embedded, for example, kind of like a substrate in integrated photonics. And this wave packet can move in this direction, and then we can change it back to the original permittivity and comes towards this, and the same thing over here. So let's take a look at these three simulations all at the same time. Let me see. Okay, here it's coming. You notice that the first wave packet is directly go to receiver 1. The second wave packet is coming over here. Let's say, oops, let's see it again. No, doesn't work. 1 second. Okay, and so it's coming, and the second wave packet, the two-step changes come over here, and the third one, again, two-step changes, but with a different delta t during the second variation that you can keep it there. I mentioned to you about that the undesirable backward wave that you see in that Gaussian beam. So how do we get rid of that backward wave? So we already showed one method, an anti-reflection temporal coating. But there's another way that we notice, actually serendipitously, by the way, we came across this when we were working on this temporal aiming. And that is, could we have something equivalent of the Brewster's angle, but in the temporal domain? And the answer is yes. Of course, we are all familiar with Brewster angle. Let's say for p polarization, when you have two dielectric at a certain specific angle, reflection would be 0, as we are all familiar with that. There is an equivalent analogy of that also in the temporal metamaterial, and that is, what if you actually change the permittivity from an isotropic single number to an anisotropic 2 values? And if your original wave has a particular angle, is it possible that that for that particular angle, the backward wave would be 0? Indeed, that's possible. In fact, analytically, we proved that through the work that we were doing with temporal aiming. We came across in our analysis, we developed and derived this expression that you see over here. Again, I don't want to bore you with the detail of mathematics, but the electric field 2 minus is the value of the electric field after this rapid change for the backward wave. So the idea is, under what condition this E2 minus becomes 0. And if you look at that condition and you go through the analysis of that, you're going to get with something that resembles, Brewster's angle, but in the temporal domain. So this would be a temporal Brewster angle we have. And the expression follows, and this is the analytical plot of this curve. So look at the expression that I showed you, the simulation I showed you before. This was the Gaussian beam that was going in the angle 15 degrees. And for that 15 degrees, that was not the temporal Brewster angle. So you have a backward wave. But if you have the same temporal variation of the material, but you actually choose the temporal Brewster angle, then you notice the backward wave is 0. So that indeed works nicely over here. Can we have a temporal wave plate? Can we play with the polarization in this case? We are all familiar with the conventional quarter wave plates, which is the birefringent plates. When you have a quarter wave plate and you send an incident wave, let's say linearly polarized with certain angle with respect to the vertical axis, this electric field, when it goes to the standard wave plates, the X component would go with a different phase velocity than the Y component. So as a result, by the time the wave gets to the other end of it, you have a different phases between the two components. As a result, you can change the linear to circular polarization, and that's the standard wave plates that you can buy off the shelf. Can we do that in time? Can we have a temporal wave plate in time in a medium? The answer is yes. In fact, this is the standard formula that we usually use for the standard, conventional wave plates. And indeed, you can do that in the time as well. In that case, the wave plate is actually a temporal time. So if you change the material from uniform epsilon, isotropic epsilon, to an anisotropic epsilon, but you hold it only for delta t, specifically, that becomes a temporal quarter wave plate, or I should say basically a temporal quarter period plate, actually, in this case. Then you're going to get an effective phase difference between the two cases, and indeed you can create any polarization you want with the starting polarization that you have there. So this shows, by the way, that if we have delta t as a half a nanosecond, and epsilon 2 y this, what should be the variation that we get as we go through, you know, different epsilon 2 xx and so on. And let me show you some of the simulation of that you see over here. You start with the, let's say, linearly polarized wave, and then you end up, you start with linear polarized wave, and you end up, for example, with elliptically polarized wave that you have over here. So this would give rise an interesting possibility to look at how this temporal variation can create some of the functionalities that we like to have in the spatial one. But the interesting point is that, of course, this variation can happen and you can change it at will. Moving along to another possibilities, and could we have some concept of spatiotemporal slab length? Now, there is a concept known called temporal lens by Alex Gaeta from Columbia University that showed how you can actually change the signal such that, you know, a signal can actually become more a sharper signal in time. This concept that we are working on is very different than that. This concept is we are taking advantage of variation of the permittivity of the material in a certain region of space in order to see if we can create a spatiotemporal slab length. Before I tell you this, let me tell you something that we were thinking about, the conventional scattering versus the time scattering. What is a conventional scattering that we are all familiar with? Well, a conventional scattering, we can call it, is also space scattering. It means you start with an unbounded medium, let's say free space, and you put certain region of space with a different permittivity. Essentially, that's our object that you put there. And obviously, if you send a wave to this object, you're going to get scattered wave. Again, this is the conventional scattering that we are all familiar with that. And if you look at the wave going in different direction, these waves have the same frequency as the incident wave, obviously, for the linear medium. But of course, the direction of the wave, different wave vectors are different, and they have different amplitude and phase, you know, in different directions. Now, do we have a temporal version of this? In other words, what would happen if we start with an unbounded medium, uniform wave, and the wave is propagating through this? And can we change the permittivity in time such that we get the scattering of that there? Well, this is something that my friend Matthias Fink has already done that, you know, in the water wave. That he has shown beautifully that if you have a tank of water and you create, you know, a wave on the surface of this water, and then when he rapidly changes, you know, the tank, in other words, this is push the tank up and down, that creates, by the way, a backward wave, as you see from his paper, and then you can basically have a time reversal in creating the image that you see there. So we were very inspired by this work, but we said, can we actually combine Matthias's approach to this, to the spatial approach of the scattering? In other words, could we have something combination of these two, space and time scattering? So we asked the following question. Imagine that you have unbounded medium, and you have a wave already propagating this unbounded medium. So this is a CW, continuous wave is going through this. And now imagine you're going to do the following. You're going to take only a certain section of the space, not all the space, only certain section of the space. And then you're going to change the permittivity of that section only from, let's say, the background permittivity to some higher value, and then you bring it back. So kind of like, you know, on and off, if you will, for the permittivity of a certain region of space. And then you can keep doing it up and down, up and down. So basically, you change the permittivity on and off. What would happen? So imagine you have that region, and this region could be several wavelengths wide. And so before I show you what the result should be, so imagine that we want to change only the permittivity of that region on and off, and we're going to do it several of this with certain temporal space between them as a function of time. So what do we expect to see? Before I show you the result, intuitively, what do we expect to see? Well, because the wave is already there, and you come over there and you change the permittivity in that region every point from, let's say, epsilon of the background to some higher epsilon and bring it back, that means at that point, you're going to actually create a dipole moment. And that dipole moment would be proportional to the value of electric field at that moment in space and time. So in other words, at that moment, you basically record the magnitude and phase of the wave inside that region, and those dipoles are all proportional to the local E magnitude and phase. But those dipoles are going to radiate, after you go on and off. So that means you can think about it that you have many, many antennas created in time right there that has the information about space and time. So what happens to the backward wave and what happens to the forward wave? Let's take a look at it. So the original wave that was coming in this region, create these sources, so to speak, and then the sources radiate forward and backward. So you notice several interesting features over here. First of all, this is something that, as you will see in the next couple of slides, actually is an advantage of the backward wave. Why? Because we're going to actually see what would happen to this expression. You notice, by the way, if this object is several wavelengths long, the backward wave and also the forward wave, it actually creates a replica of that object there, because it has all the information about magnitude and phase of this. Now, in Matthias's work in the water wave, he has that for the entire surface of the water. Here, we only have it in the specific region of the space. This is one thing we'll notice. You notice, by the way, the edges of this wave starts to diverge naturally. So if we go farther away from this, obviously this beam opens up. But it is the shape of the backward wave depends also on the original plane wave that we had. So if instead of plane wave, originally we have a cylindrical wave or we have a spherical wave, that information also is embedded in those antennas, so to speak, or those dipoles, if you will. So let's see what we can do with that. So let's say, for example, we have a slab in this case, and you send the wave in this direction, and you do this rapid change of permittivity from epsilon naught to something and bring it back. So you're going to have a backward wave coming back towards the source and the forward wave, which expected, like this. So you see that this wave is going backward in the direction of the plane wave that's coming, and this would be forward. But the problem is that if you do this, depending on the time between these pulses of variation, your backward wave may have some gap between them. So if you choose that T properly, you can actually stitch all these backward waves together and having it kind of like imitating the phase conjugation, if you will. Now, of course, that depends on the thickness of the slab, that depends on the angle of incidence and all of those, but effectively it resembles that. So if we do this for the specific shape of the region, which we call it temporal or spatiotemporal slab lens, you may be able to get a backward wave image of your original source. So imagine you have an unbounded medium. You imagine you consider a region of space that is still free space as outside. Okay, there's nothing here yet. This is just a mathematical boundary. And imagine you're going to change this region with the permittivity on and off that you can see over here. But here, your source is a line source. This is a two-dimensional scenario. You have a line source. So you don't have a plane wave, but you have a cylindrical wave. So the information about the cylindrical wave that's coming over here, plus the shape of this and this capital T period of this variation, all play a role over here. So if you do that, what happens to the wave that's coming back? Well, let's take a look at it. So here is this simulation of the total field that you see over here. But if you just show the backward wave of that, you notice the backward wave of that is actually basically coming back to where the source used to be. This actually resembles what Matthias has done in the case of water wave, but this one is coming from just a finite region of space over here. And as a result, you can make that lens different time, different things. It doesn't have to stay in that form over here. So, what's going to happen over here? If you look at basically the value of this, you notice that essentially you can have that focusing that's going back over here. and using the spatiotemporal lens that you have over here. Now, what would happen if the source is embedded in scattering? If this is, in a sense, imitating the phase conjugation, does it mean that we can actually kind of like undo the phase variation? So we put this within a bunch of scatterers that you see over here, and we repeated that simulation, and you see what happens in the backward wave that's coming over here. This backward wave is tracing back the phase and going back to the point that source used to be there. So that brings me to the final topic of my talk. And so far, what we have shown is that how this temporal variation or spatiotemporal inhomogeneity can manipulate the wave phenomena. And I showed you some of the examples, and we have done other examples too, including change of the cladding of a waveguide, for example, ring resonators that I mentioned to you, and so on. And but I just want to talk about another control phenomena that this spatiotemporal variation can provide, but not for the wave phenomena, but for the diffusion phenomena. And so what do we mean by this? Now, you're all familiar with the diffusion equation, diffusion phenomena that form, in the general equation that we have here. And we know, by the way, that if you have a standard platform and you start with some quantity, let's say it could be electric charge distribution, or it could be temperature or thermal energy, you name it. If you let that diffusion continue in time, obviously this goes, to the equilibrium, and the things will come down and become uniform, as we are all familiar. Well, we asked the following question: is it possible that this platform that we have over here would be a so-called metastructure platform or structure, such that the structure would be spatiotemporally varying, but still would be homogenized as a platform? In other words, the reason I emphasize that is that if I come over here and I make half of this platform different material than the other half, so obviously, of course, that will change the symmetry of the diffusion. That's not what we are doing. What we want to do is that we want to actually change this platform everywhere, spatially and temporally, in the proper way, that we can still look at this platform as a homogenized, from effective medium theory, homogenized platform, but then we would like the diffusion to have a preferred direction in space. Can we do that? Well, in order to answer that question, we just go, okay, how do we do this? How do we break a diffusive flow, but using homogenized medium? In other words, ideally, we would like to have something like this, that we start with this diffusion, but rather than this diffuses symmetrically, it diffuses, for example, asymmetrically, that you have over here. Now, we get inspiration also from wave phenomena, because we have done work in waves. Now, if you look at the wave phenomena, by the way, wave has a momentum. So as a result, if you look at the wave distribution, Helmholtz equation, this one, because we have this momentum, several groups have shown that if you have a spatiotemporal modulation of the medium parameters, for example, Andrew Alou has done a fantastic job in this regard, Shanhui Fan, Michal Lipson, several groups have shown that if you have a spatiotemporal variation of the permittivity, depending on the direction of the wave flow, then you can have a different result. So essentially, you break the symmetry of the structure. And in this case, in the case also, it can be the direction, breaking the reciprocity. But the problem is that diffusion doesn't have a momentum. I mean, it's a very different phenomena when we come to the wavelengths. So we decided to actually explore what we can do with this. So in order to have some physical intuition in our head, we decided to look at the charge distribution. I mean, being interested, in electromagnetics and electrical concept, we decided to look at the charge distribution, although you can apply this thing to other diffusive phenomena as well, like thermal diffusion and so on. So imagine that you have a charge distribution in a medium that has certain capacitance as a function of space and time, and certain conductivity as a function of space and time. And of course, it has to satisfy this diffusion equation. Just to get a mental image, we'll look at, this expression that we have over this transmission line we have here. But let me emphasize that this is not a standard transmission line. You notice there is no inductor there. So as a result, you don't have a wave propagation through the structure. It's only resistors and capacitors. So it's only resistor and capacitors. So if you do that, the transmission line equation is not a wave equation. It's a diffusion equation that would form over there, which represents, by the way, this equation over here. Now, so let's do the following. Let's assume the conductivity that we have over here, it's modulating in space and time, okay? With the so-called DC value, sigma naught, and modulating amplitude sigma m, and let me assume sigma m is less than sigma naught, and let's say it's varying sinusoidally, although this sinusoidal variation is not important. For now, we're just saying some periodic function. You notice that there are two other parameters over here. One is the capital omega, which is the frequency of modulation, and this is k, which is the wave number of modulation. This is not the frequency of the quantity we are interested in. The quantity of interest just follow the diffusion equation. Now, if you do that, and also we try to change the capacitance, better yet, the reciprocal of capacitance, 1 over C, so if we can change that one there. Now, you notice, by the way, here, we choose the same K, we choose the same omega, but intentionally we put a phase difference between them. And you're going to see the importance of that phase difference there that we have there. And again, GM is less than that. So what would happen if we do that? Okay, let's get this formula, put it back into this diffusion equation. Assume that sigma m is much smaller than sigma naught and GM is much smaller than G naught, okay? If you go through all the mathematics on that, you're going to find out that you can basically homogenize that diffusion equation into this form with this new quantity, which we put it with the tilde on top of it. Now, what is that? First of all, D tilde and V tilde can be expressed in terms of the parameter from the previous page. Now, you notice, by the way, this D tilde and V tilde from previous page, couple of interesting observations. First of all, you notice that the amplitude of modulation show up in both of these, okay? But what's interesting, by the way, the capital omega and K did not show up. In other words, we are assuming, we are homogenizing these things. So we are assuming that the variation in time and space are more rapid than the standard diffusion time that we have there. So that doesn't show up there. Okay, that's fine. You notice, by the way, that this part of the equation is the standard diffusion equation, but then we have this extra term, which essentially talks about the flow of some entity there. Now, this is known, by the way, as advective diffusion equation. In other words, diffusion equation that on top of that, you actually have a flow of a structure there. And this would be the effective velocity of that flow. But please note that here, we actually don't have a real flow. We're just changing the C and sigma of the structure. As a result of that, it actually looks like we have a fictitious flow that's going over there. But that flow is because of that modulation. It's not actually flow there. Now, another interesting point that, when we found, we were actually very surprised, is that you notice that this effective velocity for this, fictitious flow that you see over here, it should depend on 3 parameters that you see here. By the way, K shows up over here as well, but not capital omega. One is sigma m, so modulation for conductivity. The other one, GM, modulation for 1 over C, but also the phase difference between these two. Now, that was actually quite surprising to us, that this we will have there. So if any one of those modulation is 0 or will be in phase, we don't have this V over here, and we don't have this term over here, and we get the standard diffusion equation we have. So let's see what happens. So first, let me show you the analytical result. So here, you see the analytical, you see this flow of a spatiotemporal modulation of conductivity, a spatiotemporal modulation of inverse of capacitance. And this is the result of Q tilde, or a homogenized, a charge distribution. that we start from the original value, and you notice that it actually diffuses preferably in one direction. Now you may say, okay, this is not surprising because the spatiotemporal variation is also going from left to right. So you would think naturally this diffusion should go from left to right. But actually that's not the case, because if I go over here and I keep these two the same as it, but just change its phase from pi/2 to minus pi/2, we'll see what happens. You notice that still these two spatiotemporal modulation goes from left to right, but you notice that the diffusion, it's asymmetric, but goes towards actually the original things that you have. So it's not because of the direction of the modulation flow, it's because of the phase difference between them. And that actually is quite interesting over here. So let me show you, oh, by the way, this kind of reminds us, it's the Peristallie Pump. It's a different physics, of course, but kind of remind us. I got these things, from the Wikipedia. You notice this is a Peristallie pump that essentially can pump, the fluid, going from one path to the other. The mechanism here is different. Is because of kind of like a charge pump that we have over here that move the diffusion in the direction we want. And it also reminds us of how our digestive system works, in the sense of how the motion of our digestive system move the food. Let's look at some of the numerical results over here. So imagine that our modulation is only on conductivity, but the capacitance is not modulated. So you have something like this, and you're going to experiment in a second. So you notice that the original diffusion starts with that and just goes like this as the standard diffusion we want. So even though we have a spatiotemporal modulation of conductivity, but the diffusion still stays symmetric. Okay. Now let's do the other one. Let's stop the modulation of conductivity, but do the modulation of the 1 over capacitance. Let's see what happens. You notice here you see some minute variation that you see in the Q, but nevertheless, overall, from the effective medium aspect, they're still symmetric there. Now imagine both of them, by the way, are being modulated, but with the phase being 0. When both of them modulated with the phase being 0, you notice, yes, the underlying variation is more complicated, but still, overall, on the average, the diffusion is symmetric. What if you put a phase difference between the modulating part? Now the situation is different. Now you notice this diffusion basically diffuses asymmetrically, non-symmetrically towards one direction. And if you do the phase difference just from pi/2 to minus pi/2, you can basically control, what direction your diffusion will move there. So we decided to do the experiment on this, and we were inspired with the old-fashioned, capacitors, you can find, in the museum these days, these capacitors, that old-fashioned one that the plates go between each other and you change the capacitance between them. So we designed and built a structure like this with about, 50 plates. And these plates only partially metallized, as you can see over here. And each plate to the next plate, this partial metallization is shifted with some angle that you see there. And this metallized plate would do the job of the capacitor, but at the same time, also there's a connector over here that connects the plates. So essentially, we're going to have that RC structure that we showed there. And the handle that we have over here, if we move this handle to the left or we move it to the right, that would control the phase difference between the two spatiotemporal modulation. And then you rotate this. As you're going to see, we connect it to a motor and rotate this. So the rotation of this, the axis of this, would create this variation of the capacitance along this path, spatiotemporally. The same thing for the connection or conductivity, spatiotemporally. And the handle would give us where that connector is, so that controls the phase between them. So this is the photographs of the structure that you see. So you notice we put some of the connectors over here that we can measure the voltage coming out of this. And this shaft of this structure is connected to this motor that rotates, that you see there. And if you move the handle to this side or that side, you're going to have a different phase. You can control the phase between the two modulations. And this red dots show basically the metallization part, that each one after the other is shifted. That creates, that the spatiotemporal variation that you see. So let's look at the experimental result. If we connect the voltage source, like a battery, to one side of it, and we start rotating this, that our theory shows that the charge distribution, or equivalent of normalized voltage, which shown by these lines. Now, what are these lines? These lines, according to this color scheme, shows what happens to the voltage as a function of rotational periods, and what as a function of time. Essentially, this axis from blue to red shows the time, essentially. So that means the diffusion starts from this is the charge distribution at the source and the charge distribution at the end, and then as the time goes on, the charge builds up in this, but the charge builds up asymmetrically. In other words, the charge would go more towards the end of the structure. If you didn't have this scenario and you connect it to a battery, the charge would have been just uniformly distributed eventually. But this is not a uniform distribution, and this is the result of our experiments that we have there. So agreement is quite nice between the two, theory and an experiment. Now, in the next set of experiment, what we did, we just changed the handle from the essentially pi over 2 to minus pi over 2. So then you expect theoretically that the charge doesn't even diffuse and stays at the source. And this is experimental results that we have there. So essentially, you can control, how this charge is diffused along this structure in a very interesting way, depending on just by the phase difference between two scenarios. Remember, the spatiotemporal variation is still from left to right, always. It's just you're changing the phases between them. Now, let me show you some of the more numerical results, and then I stop. One interesting point about this approach is that because that additional term that shows up there, it's an effective velocity, not an actual velocity. What you can do is that along the structure, you can create different phases at different parts. So because this is not an actual flow of a fluid, you can actually have different sections of your diffusive system to have a different phase between a spatiotemporal one. For example, if you create one phase between this point and that point, but another phase between here and here, you can actually accumulate the charges at any point you want by this. So you can actually have very interesting trapping period of the diffusion. You can trap the diffusive quantity in the point you want, or you can deplete it from the point you want. So here, this range has a different phase than that one. You notice that then you would have depletion in the middle and the charges go to the other end. Or you can have accumulation in the location that you want. You can extend this, by the way, this was just simulation. The previous one was experiment, but this one is only simulation we showed. You can do it two-dimensionally, for example. You can think about, some two-dimensional variation of this. And let me show you the interesting. For example, you start with some charge distribution over here, and you can basically guide the diffusion to the point you want. Like this one. Possible implementation in the future we can consider is that could we do it, for example, something like this on a graphene. For example, if we put a voltage over here and we oscillate this voltage, the charge distribution along this will be different. As a result, the conductivity will be modulated. And if we have a ground plane that we can undulate, then we can actually control the capacitance between these. Just some thoughts, for the future. So that brings me to the end of my talk. I'd like to thank those members of my group who contributed significantly, directly to the result that I presented today. I'm very proud of them and I'm very thankful to them. And I'd like to thank the funding agencies provided support for us. And I would like to thank all of you. Again, I'd like to thank Bogdan, Sebastian, and Mamer, and every one of you for kind invitation to me to give this talk today. And I want to thank the audience for attending the talk, and I'd be more than happy to answer any question you have. Thank you very much for your attention.
Thank you very much, Prof. Engheta, for this wonderful talk. I think we will have many questions from our participants, so I just let them come forward with their questions. So you switch on your microphone, your webcam, and yes?
Okay, hello, can I start?